them soon. It's sort of hard to see with the glare off the floor or wherever it is there. Okay, let's get our current slide set up. Okay. 2 announcements. Treddy, you heard them both, but you haven't, so let me go over them again. Also, while we're recording, so Victor can hear them if he's listening at home. Oh, yeah, let me mark Treddy here, too. I knew you were, but I want to see the whites of your eyes. Okay. First of these is pretty important. We didn't have the whole week off. We had meetings Monday and Tuesday, and then I had office hours on Wednesday. But one of the things at the meetings they really were focusing on was this. We do have our reaccreditation visit from SACS, that's Southern Association of Colleges and Schools, the Commission on Colleges, which is what accredits us as an institution, and every other 2 or 4 year school in the Southeast. Okay, that's going to be coming up sometime in the next few years, not immediate, but sometime fairly soon. Okay, in terms of years, y'all will be gone. You don't care about it, I'm certain. Okay, but they look at data from the previous several years. And some of the data they really pay attention to are things like, not just this, but like student course evaluations. Okay? Now, we had gotten, I think, a little slack on these and just said, please do the student course evaluation, please do the. And as a result, maybe 50% or fewer students were doing the student course evaluations. That's not too good, okay? Sometimes it was getting down maybe as low as 20 or 30%. That's really bad, okay? So what they're trying to get us to do is get up to 80%. So please do the student course evaluations. If just the 2 of you do, this class will only be at 67%. So we need all of you to do the student course evaluation. Have you done them already? I think Freddie said no, you haven't either. You know how to get to it? Okay, good. Huh? Yeah, it was sent in an email, so go to that. Now, you don't have to do this before the grades come out, but the trouble is if you wait till grades come out, you're usually, I'm out of here, I'm on Christmas vacation, you know, it's sort of like Thanksgiving vacation, and you forget to do anything else. So try to get it done beforehand if you can.
One question. When is the last day of class?
We have class this week and next week, and then finals is the following week. So on Wednesday of next week, I will give you your last test, and then you take that. That's the same in the other class too. We'll probably have in the other class a test on the chapter we were on 14, and then the one on 15 is going to be very short, you know, because we won't have covered a lot.
All right.
Okay. All right. So please get those done, please.
So the next test for this class
is your final.
It's my final. Okay.
Yeah. Right. Okay. Now, in addition to that, this is sort of a more minor announcement. Normally I have office hours on Fridays, 7:45 to 11:45 on the Birmingham campus. Not this Friday. I've got an infusion scheduled for this Friday, so I'll be at the Kirkland Clinic for all day long. You know, so I won't be coming back to campus. It'll start before 7 in the morning, and it'll go till probably 4 or 4:30 in the afternoon. So no way I'll be back on campus by on Friday. So just to let you know, don't come to see me Friday. You won't catch me on Birmingham or Vassar campus. I won't be at either one. Okay. Now, don't know if you remember where we were. We were in Chapter 4, which is higher order differential equations. Okay. 4.1 was a very long section that had 3 different parts to it. 4.1 had an introductory part, 4.1, then a 4.1.1, a 4.1.2, and a 4.1.3. Okay. Now we're in 4.2. 4.2 is reduction of order. Okay. Now, since it's been a while, just to remind you, what we try to do is find another function that will help us reduce the order of the function that's difficult to deal with. Okay? and we're in the middle of page 133, and I think we're smack dab in the middle of a problem, okay? So let's go back, since it's been almost a week since we were here. Yuck, I hate to go through all this again. Let's do it fairly quickly. All right, here's what we're given. Let me get my pen set up. Oh, I can use black now, if it'll pick it up. Y1 is equal to e to the x. Given that that is a solution for this differential equation, y double prime minus y is equal to 0. Okay? Now, and that's good on the entire interval minus infinity to infinity. Okay? And you know that's true, right? Take the first derivative of e to the x. What do you have? E to the x. Take the second derivative of e to the x. What do you have? E to the x. E to the x minus e to the x certainly is 0 everywhere. In fact, that would be true if your function, your differential equation has only been y prime minus y is equal to 0. That'd been the same deal. Or y triple prime minus y. Yeah. You get the idea. Okay. But this is one. It says use reduction of order to find a second solution for y2. Second solution y2. Okay? Now, here's typically the way to proceed. Okay? Let's have y as your general function, okay, to be equal to a u of x times y1 of x. That's the one we knew already, okay? All right. Now, what we want to do is y prime. Okay, and by the way, what is y1? Y1 is e to the x. So this is u of x, e to the x. Okay? So what's your y prime? Product rule?
U x times y1 prime x.
Well, which is e to the x, right?
Oh, yeah.
Yeah. Okay?
Yeah, I'm sorry.
Is that all? Plus.
U of x prime.
Yeah, u prime of x.
And times e to the x.
E to the x also. All right, good deal. All right. Let's continue and do y double prime.
Okay, u to the x.
Second?
U to the x.
U of x.
U of x, times e to the x.
E to the x.
Plus.
Plus.
U prime of x times e to the x.
Okay.
Plus u, the y to u prime of x
U prime of x.
times e to the x.
E to the x.
Plus u double prime of x times e to the x.
Very good. And we can simplify that a little bit by saying u x. You know what I'm going to do? Just want to do u of x plus 2u prime of x plus u double prime of x times e to the x. Because everything's by e to the x, right?
Yeah.
So, going to get that separated like that. Okay. They left them all in there together. I don't see why they did it. So now let's go back to our differential equation, which will be this thing, u of x plus 2u prime of x plus u double prime of x e to the x, that's the y double prime from above, minus the y, which is here, u of x e to the x. Okay, set that equals 0. Okay, that's from your differential equation. Okay, now, if you'll notice there, this is u to the x times e to the x, and this is minus u to x times e to the x, right? Yeah, I just didn't do that. So that now what we have is 2u prime of x plus u double prime of x e to the x is equal to 0. Okay. Now, they put the e to the x in front, I put it behind. It doesn't matter. And they left off the of x's in there too. Now, one thing we know is that e to the x can never equal 0, right? Yeah. So, you know that the product of these two things has to be 0, means one or the other has to be 0, right? But this one can't be 0, so therefore this tells us this is true. 2u prime plus u double prime is equal to 0. Okay, so that's what we can conclude from that. Okay, now notice we don't have the u in there anymore, just u prime and u double prime. So here's what we do. This is where the reduction in reduction of order comes from. We'll let, and they usually go with w. Is that what they use here? Let me find it. Yeah, w equals, let w equal to u prime. I swear this is such a pain. So this would then be 2w plus, and then w prime is equal to u double prime, right? Plus w prime is equal to 0, right? That's your reduction in order, okay? You started out with a second order, now you're at a first order, okay? You've already got one solution. This is going to find you another solution. There's only one solution for a first degree, first order differential equation. Usually one general solution thing. Second order, you'd have two. Well, second order that you first started with, they gave you one, we're finding the second one. Okay. So, I'm sorry, we did this problem completely. I am so sorry. I thought general case followed this. This is not the same solution. Sorry about this. Let me erase all this. This was a review, okay? Just seeing if you remembered what we did before Thanksgiving. I obviously didn't. I have my mark here, but I was thinking, why are we doing this again? Well, we're not. We are going to repeat some of what we did last time, but here's where we should have been starting. Okay. Suppose we divide, okay. You have to go back to the very beginning of chapter 4, okay? And they gave you that initial value and boundary value problems, the initial value problem, and it had a sub n, dn, the nth derivative of y with respect to x plus a n minus 1 of x, and all like that. And then they say, let's divide that first form into, and we're going to use second order partial differential equations only now. Not partial, second order differential equations only. I'm getting in partials from Cal 3. But sorry about that. Didn't mean to. So I guess you would say the general form for the other was a2 of x d2y dx squared plus a1 of x dy dx plus a sub 0 of x y is equal to 0. Excuse me. Sorry. Y'all awake yet? All right. Poor Victor, if he was listening at home, he had no idea that was coming, did he? All right. Oh, I'm sorry. All right. If you go back to the first of the section, that's how we define a second order differential equation. They did it in nth order, but this is second order. Okay? These coefficient functions are of x alone. No y's in them. There is a y there, but that's the only place. Goodness, I may have to sneeze again. Sneeze at home, my wife screams, the dog jumps. It's terrible. Okay. Sorry. This is loosening things up. In the last class, I felt like this air coming down was incredibly dry, and now it has me sneezing. I don't know what's going on. Hold on just a second. Sorry. All right. You've seen something like this before. Hopefully you remember it. To get this into our what they call standard form, where that was sort of like a general form, let's divide everything by a2 of x. Okay, number one, a2 of x can't be 0 for this to be a second order differential equation. Because if a2x was 0, that'd be a first order differential equation. So a2x can't be a 0 for any value for x in the domain. Okay? So we'll divide everything on both sides by a2 of x. Okay? I don't know where these things come from. Okay. Now, obviously this goes to 1. So you have d2y dx squared. Okay? Now, plus. Now, in the old days, p of x stood for a polynomial. That's not what it's standing for now. This p of x is a rational function. Okay? In fact, it may be far more complicated than that. But it's just the quotient function, the ratio of those two functions, that's our p of x. dy dx, and this we'll rename q of x. And again, that's not necessarily a polynomial function. In fact, the odds are it's not a polynomial function. It could be, okay? But 0 divided by a2 of x is just 0. All right. Now, that looks a lot like what we used to call a linear differential equation, doesn't it? Okay? And there's a reason for that. Okay? Yeah, well, anyway, we won't go redo any of that. Okay. Now, what is required here is the p of x and q of x now have to be continuous on some interval I. Okay. Now let's see what that implications that has. We just divided by a2 of x to get there. So, and I already said that a2 of x can't be 0 anywhere on the domain. Otherwise, that wouldn't be a function. It wouldn't be a second order differential equation then. Okay. This now requires that continuity requires that there can't be any places where your domain is not, there can't be any vertical asymptotes. There can't be any holes in the function. Can't be. And basically, those are the place where the A2s would be equal to 0. So they don't happen, okay? So A2 can't be equal to 0 anywhere in the domain. So basically, that's another way of saying this domain can't include any zeros for the function A2. Because if there was a 0 there, then you'd be dividing by 0, and this would not be a continuous function here or here. So we are requiring those to be continuous. So we have to be places where A2 of x would not equal 0. Okay. All that is saying the same thing. All right. So why am I saying it again? Let's further suppose that y1 of x is known. Somehow you know that is a solution to this differential equation. That is a known solution. Okay? y1 of x is a solution. Okay. And also, it carries with it that y1 of x cannot equal 0 for every x in the interval. In the interval I, where that was defined. Okay? Oh, I didn't write this. P of x, I talked about it but didn't write it. Q of x, continuous on I. That's the interval in which they are continuous. Okay. So let's do something very similar to what we did before. Let's come up with another solution y, and that will be a u of x times y1 of x. Okay? Now, let's take a first derivative of that. y1, y prime of x, we'll probably leave off the of x's after a while, would be what? Get it again. Yep.
Where's
There's y.
Okay. That would be u.
U.
Oh, u times the
y1 prime.
Yeah, y1 prime
Plus.
u double prime.
U prime.
Yeah, u prime
y1. y1. Okay, very good. We need one more. So y double prime. Put of x, but we don't need it. I'm not going to write that always. What will that be?
That would be
U
times y double prime.
y1 double prime.
And plus. Gosh, I keep confusing myself.
What's that?
I keep confusing myself.
Okay. Let me confuse you. Okay.
Y, yeah, go ahead.
U prime, y1 prime, plus yes, U double prime, y1, U prime, y1 prime. Very good. And notice we got two of these again. So this can be shortened to be y double prime of x is equal to u y1 double prime plus 2u prime y1 prime plus u double prime y1. All right, so there's your y double prime, okay? Now, if we put all these together into our differential equation, which is this one right up here, there's your y double prime. That's going to be d2yd, that's this one. So that's going to be u y1 double prime. You see why I start leaving out the x. It would be way too long if I wrote of x for every one of those. Plus 2u prime y1 prime plus u double prime y1. Okay, that's this one, plus p of x, goodness gracious, this is a pain in the neck, time your y prime. Here is your y prime, and that would be u y1 prime plus u prime y1. Okay, plus q of x times y, which is u y1. Okay, that was your y. And that this is equal to 0. Okay, now I'm going to do a sleight of hand here. Okay, I'm going to group terms carefully here, and I'm going to do u y1 double prime, skip this one for now, and skip that one for now, and do this one, plus I'm going to rearrange the order a little bit, u p of x y1 prime, plus, I'm going to skip that next one for now, q of x u y1, plus, now let's go back and pick up the ones I left out, 2u prime y1 prime, okay, plus u double prime y1 plus p of x, okay, I used that first one over here, so let's do the second one here, times u prime y1, and that's equal to 0. All right. All I did was rearrange the order of the terms, right? Now I want to point something out to you. We said that y1 is a known solution for that differential equation, right? That means that y1 double prime plus p of x y1 prime plus q of x y1 is equal to 0. It's a known solution, so that would make it true, right? So what do we have here? If we factor out a u here, well, let's do that. In these first three terms, u times y1 double prime plus not important, but let me write it in the right order. One of these days it'll erase, okay. P of x y1 prime plus q of x, because I factored out the u, y1, okay, plus all the rest of that is equal to 0. But guess what? This thing right here, by what we said before that y1 is a known solution, this is equal to 0. So we can throw that away. That's equal to 0. So all we have left now is this part. Okay? And that is So that's all equal to 0. Okay. So now we have 2u y1 prime plus u double prime y prime, y1 prime, plus p of x u prime y1 is equal to 0. All right. Now, sorry about this. I got to erase some stuff at the top. And I hope I'm not going to need some of this again. I sort of want to leave my first equation there, but I really don't need that anymore. So let's get rid of it. And even though my eraser is here, it's not doing a thing. Ha! It did something. Okay. All right. Now, we're going to do the little trick. I happen to notice that prime didn't make it in here. 2u prime y1 prime plus u double prime y1 prime plus p of x u prime y1 equals 0. That, I keep seeing things that are wrong in this. I thought that can't be. That's yuck. That's not a prime there. Okay. Nor there. Okay. Because remember, let me make sure of that. Let me do my pen back. Okay. We took out that term. Okay. We had this term, which was that one. We had this term, which was that one. That doesn't have a prime in it. And the first term here we used, but the second term we didn't. Okay, so that's fine. And we used the last term. Yeah. So that's what we needed to have. Now, notice here again, we've lost our u's here. Okay? We only have u prime, u double prime, and u prime. So, reduction in order. We'll let w equal u prime. Okay? Then, let me do it that way. Yuck. W prime is equal to u double prime. You buy that? I don't know why this keeps doing that, but it's a pain in the neck. So let's rewrite our equation now. 2w, which is u prime from before, y1 prime, plus u double prime is now w prime, y1, plus p of x, w, which is y prime, u prime, y1 equal 0. Okay, that's substituting in w for u prime, which makes w prime u double prime, and we substituted in this last part down here and got that. All right. Now, okay, if we were to divide everything here by 2w, I think that is what they do next. even easier than that. Okay. Let me make sure I have all my terms here. Oh, I was going to say, I can't find the things here. I was looking at the wrong line. Okay. So this is y1 w prime. That's the one they do first, plus 2 y1 prime plus p of x, p y1 times w. Okay. Let me rewrite this. Everything is so slow. I'm trying to write it in the same order they do. Okay. So we'll take this term first and write y1 w prime. Okay, plus, okay, now I'm going to separate out my w, so this will be 2y1 prime plus p of x y1 w is equal to 0. Okay, I think I have it the same way they do now. Yeah. They don't put the x's in there, but it's fine. All right. Now, what they're going to do next, and let me erase some. This is sort of a pain in the neck. Well, my eraser acts like it's going over the page, and you can probably see it. And then after a while, things start erasing. Except they all didn't erase, so let me get those two done. Okay. This is such a pain. Okay. Now, what they say, they say that this function here is separable, a separable function in W. Okay? Now, this is where things get a little hairy here, is that they kind of start ignoring the x's. Well, they can't really, but it gets a little bizarre here. What we're going to do is divide everything here by y1. Okay. And we'll also divide everything by w. Okay. So this first term becomes, now obviously now y1 can't be 0 on the interval also. So you have w prime over w plus 2y1 prime over, and the w's cancel out here, divide out there. Okay. 2y1 prime over y1 plus p of x, and they don't carry the x's around with them, probably I shouldn't either, plus p of x is equal to 0. Okay, because see, the y1s cancel out there, but they don't. You know, you got to keep it in for that. Okay. So this is what they call a differential equation that's separable. You have your w's here, and then the functions of x is there. Okay? This is dw dx, and the w of x, and then you have 2y1 dy1. Yeah. That p of x is sort of a pain in the neck there. Okay? They say it's separable, but it isn't as obviously separable as what I think it should be. Okay? But what they do is write it in all right. This is dw dx over w plus 2 dy1 dx over y1. Okay? Plus p of x is equal to 0. Okay? All right. Now, what they're going to do is multiply everything by dw. I mean, you're not supposed to, a dx. You're not supposed to talk about it that way, but that's what they're doing. And that gives you, I'm going to erase some more here. Sorry. Yeah. This is so slow to erase. All right. All right. Multiply everything on both sides by dx. Okay, so this leaves you dw over w plus 2 dy1 over y1, okay, plus p dx, okay, because we multiply everything by that is equal to 0. All right. Now, that gives you to me, that would be the most logical way to write this. However, they keep a dx in there with the y prime. And to me, it's somewhat useless. I mean, why do that? Okay. Now, sorry. I really don't like their procedures here. It looks like they're really skimping on things. But what you have here, if you had done it my way, okay, which you may say, this is obviously all x's there, right? Right here. This is all w's and that's all y's. So in that sense, we've separated the variable, the x terms and the wy terms, okay? But if you integrate this with respect to, and this is not real clear, So I really don't care for their presentation here. Let me erase another line down here so we can have more to work with. I hope we don't need to go back and find this. Well, finally erased. Now, I don't care for the way they're doing it, but they're lumping together these two and saying they're integrating those, okay? This would be a log W, right? And this would be plus 2 log Y1, right? And this would be let's move that to the other side and make it minus the integral of P of x dx, okay? Now, again, really shaky here, but this is dy w dx. Integrate this with respect to w, integrate that with respect to y, integrate that with respect to x. We can't do that because we don't know for sure what that dx is, but leave it in that form, okay? What do we have here? Well, you could rewrite this as log w plus log y squared, y1 squared, is equal to minus the integral of P of x dx. And why my pen is so slow catching up, I don't know, okay? Well, now you can combine those two as the log of w y squared. Okay, now, at this point, they start putting these in absolute value bars. And they really should have on the previous line as well. Well, they didn't write the previous line as well. Okay, but I should have done it here, made sure that's absolute value. And I don't see why they would have messed with that at all. They didn't, because y1 squared is always positive. Okay, but when you combine those two together, it's log of wy squared is equal to minus the integral P of x dx. Okay? I think I'll erase another line. This is such a pain. In fact, I think what I'll do is I'll erase all the rest of it. I'm tired of doing this piecemeal. Okay, let's see if any of that disappears now. Don't get rid of it. Okay, let me do some more. Okay, let's see if any of that disappears now. Looks like we're still left with one here, here, and here. All right, finally. Okay. Now, what we have here, we can do e on both sides. Take the exponential of both sides of the equation. The exponential of the log would just give us w y1 squared is equal to e to the minus integral of p to the x dx. Now, hopefully that looks a little familiar. Does it? That was our integrating factor. The right-hand side was our integrating factor back when we did linear differential equations, right? I think we usually called that something, but we believe it was w. We can't call it w anymore because we already used the w. So they're going to call it u, okay? I can't even, yeah, we had u's at the very beginning, but it's a different u from that one, so it seems like that's really a poor choice. Well, maybe you're okay. All right. One exception here, you have to have a plus C. Okay. The reason for that is you had you're integrating, and you have to have a constant for that one integration. Okay. Now, and again, they've done it really, well, I'm sorry. Here's the plus C up here. I thought they've done it really poorly, but I was the one that wrote it on the wrong line. Okay. All right. Now, they're skipping a lot of steps here, and I'm trying not to. When they take the E of this side and that side, well, E of the sum is E of this, E of this, E of this. We wind up with the sum here, same base, different exponents, combine them together. That gives you a different C. We'll call it, I think they call it C1. Yeah, C1. Okay. E to the minus that. Okay. Now, what they're going to do next is divide both sides by y1 squared. Okay. And when you do that, you get that to be w. But if you remember, w was u prime. So they didn't just use any old u. That is the right one. So now we have that u prime is equal to c e to the minus integral p of x dx divided by y1 squared. Okay. The only thing is they put that, yeah, that works. Okay. Now, next thing they do, they write this as du dx. Yuck. Okay. And then integrate that, in other words, multiply both sides by dx, write it as a differential. That gives you u is equal to the integral of c1 e to the minus integral of p of x dx over y1 squared. Okay, and then you have a dx here too. So it looks rather bizarre. Okay. Now, what they make this u to be is your new function y2. Okay? All that time, they now say, just let that be, well, wait. That's not quite fair. Let me put in one more step there before I do that. Okay? That's what it looks like they do, but they didn't quite do it that way. When you integrated that, you got another constant, C2. Okay? When you integrate this, you get U. And when you integrate that, you get the integral of all that you had before plus C2. Okay? Now, here is another part. To me, they're really mushy on. They say, let's let the C1 here be 1 and the C2 here be 0. I guess they can let it be anything they want to. They're arbitrary constants. And if you do that, that then gives you we don't have it on the board anymore, but if you remember from the very beginning, we said that y2 is equal to u times y1. We may have just said y, but we can now designate that specifically as y2. And if you put, that would imply that u is equal to y2 minus, divided by y1, and that would then be y2 divided by y1 is equal to this integral of c1 e to the minus integral p of x dx over y1 squared, I'm sorry, yeah, y1 squared. That's all we have to do. Okay, dx, I left off my dx there. There's a dx up there for that integral, but then one here for this one too. Okay? Now multiply both sides of the equation by y1. Now this isn't under the integral. Now you have the new function. Why the y didn't show up here, I don't know. There's your y1. Okay. That is their solution to the original problem. They gave you one solution, y1. Here's your second solution. Now notice what you did. You just took that p, that middle term there, that's the only one, integrated it just like we did back with linear equations. Integrate that. Whatever that integral turns out to be, you don't need a plus c or anything for that. Whatever that integral turns out to be, e to the minus that, there's your one embedded constant. This is over y1 squared, so you can put those in. Outside the integral, there is a y1 there too. You can't cancel these because this one you're integrating, this is just multiplied through by that integral. So don't try canceling that. These are dependent on x as well. But whatever that gives you, that's your new second equation, solution y2. Okay. Now, goodness gracious. It says it makes a good review of differentiation to verify the function y2 of x to find right there satisfies equation 3, which is our original differential equations I've already erased, and that y1 and y2 are linearly independent on the interval in which y1 is not 0. Okay. Wow. What a pain. Example 2 is going to use that same kind of thing, so let's see if we can get it done. I don't know if we can. Let's give it a shot. Here's a y1 equal x squared. Okay? It says that is a solution for x squared y double prime minus 3x y prime plus 4y equals 0. Okay, there's your differential equation. It says find the general solution of the differential equation on the interval 0 to pi. 0 to infinity. Okay. Notice 0 is not a solution. X cannot equal 0. Why? Because then this term would be 0, that term would be 0, 4y equals 0, that would be a very interesting differential equation. It wouldn't even be a differential equation. So you have to not allow x to be 0. So therefore we start anything past 0, not 0, that's not a bracket, it's a parenthesis, anything, any positive value for x, this will be a differential equation. Okay? Can't be 0. Okay. Now we need to verify that one solution would be y1 equal x squared. Well, let's do it. y1 prime is equal to what? 2x. And y1 double prime is equal to 2. Right? So this will be 2x squared, because y double prime is 2, minus 3x times y prime, well that would be minus 6x squared, right? Plus 4x squared. Is that equal to 0? Well, 2x squared plus 4x squared is 6x squared minus 6x squared is 0. Yes, it is. That is 0 anywhere from x greater than 0, any positive 0. Okay, so we know that solution does work. All right, now, from the standard form of the equation, what we're going to do is divide everything by x squared. So that will be y double prime minus 3 over x y prime plus 4 over x squared y is equal to 0. We divided everything by your leading coefficient function, divided by x squared. Got it? Yeah, we divided this by x squared, that by x squared, that by x squared. Okay? Now, this was our p of x, right? All right. Remember what we did? We did the integral of p of x dx. That would be the integral of 3 over x dx. And that would be what?
Log
3 log x. Very good. Okay. You don't need a plus c on this one. Okay. And then what did we do with it? We did e to the minus integral of blah, 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 p of x dx. Okay. So that would be, well, let's make this the log of x cubed. Right?
Yeah.
Okay. And when you do e to the log of x cubed, you get x cubed, right? And this is equal to x cubed. So that's our, what you might think of as the multiplying function, okay? Now, our y2, from what we did before, I've erased it now, but y2, remember, was y1 times the integral of this e to the minus well, we've already done this. That would be x cubed. That integral of this thing that we did before, that comes up being x cubed over, now they say x to the 4th here. Now where did that come from? That's your y1 squared. Remember? That was what was down here. So y1 squared is equal to x to the 4th. Okay? Well, yuck. This comes out being y1 times the integral of 1 over x dx. Okay, now we had a constant in there. Oh, they set it equal to 1, remember. Okay, we'll live with that. So this is y2 is equal to y1 log x, plus some constant c. But they're leaving off that constant c, making it 0. So, okay, we'll do that. Okay? Well, what was y1? It was x squared. So your y2 here is equal to x squared log x. Okay? Now, your general solution then would be y is equal to c1 x squared, that's your first one here, plus c2 x squared log x. Okay? There's your two-parameter solution for that differential equation. If you had time,
Is that a plus between?
it is a plus, and I don't know what happens to, for some reason, sometimes the pen doesn't write. I was just looking at the same thing. C1x squared plus C2x squared log x. Okay? And there, you can take the first derivative and the second derivative of those, plug them in, you will get those two solutions. Second order differential equation, two-parameter system should be your solution. And that's indeed what we get. C1 x squared plus C2 x squared log x. All right. There is a remarks at the top of the next page, then the homework exercises, any of the odds 1 through 15, either 17 or 19 or both, and do 21. Okay? Those are the only ones you have to do. You can read through the discussion to see if you know what they're talking about. You don't have to. And then the computer lab assignments, we don't have a computer lab, so you don't have to do that either. Next time we'll start with homogeneous linear equations with constant coefficients. Whew. Okay, we finished 4.2. Unfortunately, I had to cover way more of what we had done last time, otherwise we'd already been in there. Okay, I think we did barely go over, but we're all right with it. Any questions? All right, let's go on. Oh, that's not what I want to do. I want to save